Hello and welcome back to Steve and Data. Today in this video I want to talk about conditional probability. It is an important topic in probability because sometimes probabilities need to be re-evaluated as additional information becomes available. Consequently, we should know how to calculate the new probability, and this is where conditional probability comes to help us. Although it is a simple topic, you will face it in real-world problems a lot. So pay a lot of attention to this video to learn it thoroughly. As I said, sometimes probabilities need to be re-evaluated as additional information becomes available. A useful way to incorporate additional information into a probability model is to assume that the outcome that will be generated is a member of a given event. This event, say A, defines the conditions that the outcome will satisfy. Then, probabilities can be revised to include this knowledge. The probability of an event B under the knowledge that the outcome will be in event A is denoted as this, and this is called the conditional probability of B given A. Now let's see some situations in which we can see the logic of conditional probability. A digital communication channel has an error rate of 1 bit per every 1000 transmitted. Errors are rare, but when they occur, they tend to occur in bursts that affect many consecutive bits. If a single bit is transmitted, we might model the probability of an error as 1/1000. However, if the previous bit was in error because of the bursts, we might believe that the probability that the next bit will be in error is greater than 1/1000. In a thin film manufacturing process, the proportion of parts that are not acceptable is 2%. However, the process is sensitive to contamination problems that can increase the rate of parts that are not acceptable. If we knew that during a particular shift there were problems with the filters used to control contamination, we would assess the probability of part being unacceptable as higher than 2%. After seeing the circumstances that which conditional probability can be applied to solve a problem, it's time to see an example. In a manufacturing process, 10% of the parts contain visible surface flaws and 25% of the parts with surface flaws are functionally defective parts. However, only 5% of the parts without surface flaws are defective parts. The probability of a defective part depends on our knowledge of the presence or absence of a surface flaw. Let D denote the event that a part is defective, and let F denote the event that a part has a surface flaw. Then we denote the probability of D given or assuming that a part has a surface flaw as this. Because 25% of the parts with surface flaws are defective, our conclusion can be stated as the probability of D given F equals 0.25. Furthermore, because F prime denotes the event that a part does not have a surface flaw, and because 5% of the parts without surface flaws are defective, we have the probability of D given F prime equals 0.05. You might get confused by the calculation of last probabilities, but don't get afraid. With the following example, which is the numeric version of our example, you will completely figure out where those probabilities come from. This table provides an example of 400 parts classified by surface flaws and as functionally defective. For this table, the conditional probabilities match those discussed previously. For example, of the parts with surface flaws, I mean these 40 parts, the number of defective ones is 10. Therefore, the probability of D given F is 10 over 50, that equals 0.25. And of the parts without surface flaws, I mean these 360 parts, the number of defective ones is 18. Therefore, the probability of D given F prime is 18 over 360, that equals 0.05. In the last example, conditional probabilities were calculated directly, but the problem is we won't always have these numbers to calculate conditional probability like this. In this case, these probabilities can be determined from the formal definition of conditional probability that says the conditional probability of an event B given an event A denoted as this, and it is equal to probability of the intersection of A and B over the probability of A. But remember one thing, because the probability of A is in the denominator, it must be greater than 0. This definition can be understood in a special case in which all outcomes of a random experiment are equally likely. If there are n total outcomes, the probability of A equals number of outcomes in A over n. Also, the probability of the intersection of A and B equals number of outcomes in the intersection of A and B over n, and consequently the probability of B given A equals number of outcomes in the intersection of A and B over the number of outcomes in A. Therefore, this conditional probability can be interpreted as the relative frequency of event B among the trials that produce an outcome in event A. Now, let's calculate the last probabilities with the formal definition of conditional probability. Again, consider the 400 parts in the previous table. From this table, we have the probability of D given F, that equals the probability of the intersection of D and F over the probability of F. And it is equal to 10 over 400 divided by 40 over 400, that equals 10 over 40. Here we can see all the remaining probabilities, and note that in this example all 4 of the following probabilities are different. Here, the probability of D and the probability of D given F are probabilities of the same event, but they are computed under 2 different states of knowledge. Similarly, the probability of F and the probability of F given D are computed under 2 different states of knowledge. This tree diagram can also be used to display conditional probabilities. The first branch is on surface flaw. Of the 40 parts with surface flaws, 10 are functionally defective and 30 are not. Therefore, the probability of D given F is 10 over 40, and the probability of D prime given F is 30 over 40. Of the 360 parts without surface flaws, 18 are functionally defective and 342 are not. Therefore, the probability of D given F prime is 18 over 360, and the probability of D prime given F prime is 342 over 360. But before wrapping up the video, let's check another subject that is related to our previous video, which was about sampling. When sample spaces were presented earlier in the random experiment and sample space video, sampling with and without replacement were defined and illustrated for the simple case of a batch with 3 items of A, B, and C. If 2 items are selected randomly from this batch without replacement, each of the 6 outcomes in the ordered sample space, AB, AC, BA, BC, CA, and CB, has the probability of 1 over 6. If the unordered sample is used, each of the 3 outcomes, A and B, A and C and B and C has the probability of 1/3. When a sample is selected randomly from a large batch, it is usually easier to avoid enumeration of the sample space and calculate probabilities from conditional probabilities. For example, suppose that a batch contains 10 parts from tool number 1 and 40 parts from tool number 2. If 2 parts are selected randomly without replacement, we are interested in the conditional probability that a part from the tool number 2 is selected second, given that a part from tool number 1 is selected first. Although the answer can be determined from the counts of outcomes, this type of question can be answered more easily with the following result, which is called random samples. The random sample says to select randomly implies that at each step of the sample, the items that remained in the batch are equally likely to be selected. So, if a part from tool number 1 were selected with the first pick, 49 items would remain, 9 from tool number 1 and 40 from tool number 2, and they would be equally likely to be picked. Therefore, the probability that a part from tool number 2 would be selected with the second pick, given that the first pick was from tool number 1, is the probability of E2 given E1, that is 40/49. In this manner, other probabilities can also be simplified. For example, let the event E consists of the outcomes with the first selected part from the tool number 1 and the second part from the tool number 2. To determine the probability of E, consider each step. The probability that a part from tool number 1 is selected with the first pick is the probability of E1, that equals 10/50. The conditional probability that a part from the tool number 2 is selected with the second pick, given that a part from tool 1 is selected first, is the probability of E2 given E1, that equals 40/49. Therefore, the probability of E equals 40/49 times 10/50, that equals 8/49. And finally, always remember this point. Sometimes a partition of the question into successive picks is an easier method to solve the problem. Now, it's time to wrap up the video by reviewing what we have learned so far. First, we saw that sometimes probabilities need to be re-evaluated as additional information becomes available. And to calculate this new probability, we use a concept called conditional probability. Then we saw that we can directly calculate this probability in some rare cases, but generally we use the formal definition of conditional probability that says the conditional probability of an event B given an event A denoted as this, and it is equal to probability of the intersection of A and B over the probability of A, which is always greater than 0. And finally, we learned something about random samples that says to select randomly implies that at each step of the sample, the items that remained in the batch are equally likely to be selected. And that is done. Congratulations! Now you know some information about conditional probability and you are able to solve complicated problems with the help of it. At last, if you like this video, please hit that like button, and if you are interested in probability, statistics and data science topics, please consider subscribing to this channel. By the way, if you have a question about this subject and anything related to the fields I mentioned, comment it down in the comment section. I will answer them as soon as possible. I hope this video helped you a lot, and until the next video, happy learning!